Hello everyone, myself Kirish with Solidworks tutorials. Today I'm here with the simulation tutorial that is on fatigue analysis on basketball ring. Okay, so before getting into this exactly the fatigue analysis, we'll go ahead with the basics. So it basically originated from a Latin word that is fatigue, which is known as to tire. Okay, so everyone will get tired, no? Same thing after a certain amount of time, whatever the material or whatever the component we're gonna consider, it will go to tire. Okay, the terminology is a damage and failure of material under the repeated cycles. Okay, that is cyclic loadings. So this is all about the basics. You can just go with this. So it is just a progressive, localized, permanent structural change that occurs in the material subjected to the fluctuating stresses and the strains. Okay, that will directly leads to the crack propagations after a sufficient number of fluctuations. Okay, so there might be high fatigue cycles and low fatigue cycles that we'll see now. Okay, so these cyclic stresses are normally well below the yield strength of the material. Okay, so we're gonna consider only the fatigue analysis that will lie under the yield strength. Okay, if you're considering high fatigue cycle, so that will be under the same thing. So as you could see, this is the cyclic loading. Okay, this is fully reversed. Okay, it is 1 to -1 you can consider. There might be some cases zero biased, that is zero based as well. So it will, like, initially it will load up to a certain loading condition. Let's say from 0 to 1. Let's say I'm applying the 500 Newton, 0 to 500 Newton, and again it will come to rest. In the sense, the loading will be removed. It will not be again minus 500 Newton downwards, as you could see in the curve. Okay, that is 0 to here, like this. So that is known as zero based. Okay, so there are different types of fatigue failures. One is the mechanical fatigue, that is due to fluctuations in the external applied loads, that is stresses and strains. Due to this stresses and strains, due to this the fluctuations will be created, that is known as the fatigue, that is mechanical fatigue. The creep fatigue, in the sense, due to the high temperature with the repetitive loading conditions. Okay, same thing, we have thermomechanical fatigue, the fluctuation in the temperature as well as the stress and strains, everything will be considered there. The corrosion fatigue, what exactly it is the cyclic loads in a chemical aggressive and embrittling environment. And then we have the fatigue. Okay, this is a cyclic loads combined with the frictional sliding as well. Okay, so these are the few things, and the same thing will be explained here. Low fatigue cycle, which and all will be considered, and the high fatigue cycle, and this is the endurance limit. This we'll see in detail in the next slides. Okay. Yep. So here there are some description about the stress strain curves. You need to remember, if you're going to deal with the fatigue analysis, we need to know about the stress versus number of cycle curves. So that is mandatory. And with respect to that, some of the rules will come into account. That is criterias. That is Goodman, Gerber, and Soderberg, and Brown Millers, and there are different criterias are there. So here the first thing is we have the number of cycles. Okay, it is e raised to 7, that is, you could see 10 into 10 raised to 6, or e raised to 6, e raised to 7. We can call it as 10 e raised to 6 or 1 e raised to 7. So this is the maximum cycles we're gonna consider for the fatigue analysis. Okay, if it is more than that, it is high fatigue cycle. If it is less than that, it is low fatigue cycle failure. Okay, so as you could see, the low cycle, in the sense, there will be high stresses in the model. Okay, which will be due to the plastic deformation, not in the elastic region. So these are the low fatigue cycle. Okay, there will be high stress. Due to that, the elastic deformation will happen, and with that, the fatigue failure will occur. So this is the some description about it. We can just go through this one. And coming to the high fatigue cycle, so there will be a low stress fatigue, we can say this one. So here what exactly happens is the whatever the deformation will be there, no, the fluctuations will be there, it will be in under the elastic range. Okay, as you could see, material deforms elastically. The same thing, there are some explanations, you can just go through this. Yep. So there are some things, that is crack initiation and crack propagation and the ultimate failure and all, and the crack growth. So that and all the basics are there, you can just go through it. Coming to the ascent curve, as I said, so the behavior of the material in the high cycle fatigue is characterized by the relations between the alternating stress and the corresponding number of cycles to the failure. So this is represented here in the uh, graph. So as you could see, this is 10 raised to 6, in the sense e raised to 7. It will be the fatigue strength of each and every material. So this endurance limit, you could see, it is 10 raised to 7 is the cycle. So we can consider, if your component has the fatigue cycle more than 10 raised to 7, your model will be safe enough. Okay, it will it has the higher lifespan, so unlimited lifespan we can consider. Okay, yep. So these are the approximations points you could say. This is the practical testing we can consider. Depending upon that, this curve will be drawn with respect to approximation. Okay, so from this only we're gonna get the stress versus number of cycle curve, and that will input into the fatigue analysis to get the results accordingly. Remember that. Yep. So coming to the fatigue strength, as I explained, this is the stress at which the stress failure occurs at the given number of cycles. Okay, the failure will occur at the number of cycles, and is known as fatigue strength. So that much cycle it will withstand, in the sense after that it will fail. Let's say 50,000 cycles, so that is the fatigue strength of the model, that is 50,000 cycles. After that it will fail. So endurance limit is the limit where you can consider it as the unlimited lifespan, that you could see. Endurance limit is the highest alternating stress that does not result in the fatigue failure, that you need to keep in mind. Okay, in short, you can go through this all the details, or you can read it to understand more. Okay, you could see we have the fully reversed stresses as well. Okay, coming to the criteria, so first one is the Goodman criteria, which we consider for the brittle materials. As you could see the curve here, this is the Goodman criteria curve. So if you're dealing with the brittle materials, better deal with the Goodman criteria to deal with this. We have the Gerber, that is experimentally known as that is tactile, that is only meant for the ductile materials. Remember that, Gerber. The Gerber curve, you could see here, this is the curve which is used to deal with the ductile materials and the Soderbergh. So it is the curve which we will refer when yields conservative results in the tension. Okay, so you could see these are all the curves and how they gonna implement on the results. Yep, this is the basketball ring model. So on this, we're gonna conduct the analysis. I'll break the links. So once you are done with this, you can activate your SolidWorks simulation add-in in the SolidWorks software. Once you do that, depending upon the license which you had for the simulation, that is SolidWorks simulation standard, professional, and premium, according to that you'll have the capabilities. So you could see I'm having the SolidWorks simulation premium. I can able to access each and everything here, including static to nonlinear analysis. So I'm gonna deal with the fatigue analysis. So you can just give the naming to the project analysis, and you can simply hit on green check. The study tab will be created. So now the first thing is you need to assign the material. So from apply material tab, you can able to access the number of materials with respect to the different types of metals, okay, and even alloys. So we have the Solidworks material database. The large data is available, so you can utilize the same thing. So at the moment, to deal with the fatigue analysis, we need the material which has the SN curves. Okay, so for that, I'll choose the aluminum 7075T6 with SN curve material. Okay, so even you can use the different materials which had used uh, the materials the data from other softwares that you can manually input. So I'll fix this face, and I'll simply apply the load on this face. Okay, so you can select the force, and on this face I'll take it 100 Newton at the moment. Okay, so later on you can change it. So with respect to this, I'll simply mesh it. So in the meshing, you can refine your mesh by using the mesh parameters. I'll use the advanced blended curvature based mesh. I'll define the global size as 5 and the ratio as 1:2, 1 by 2. So 1.2 it is. So once you mesh it, you could able to see how precisely it will be meshed on the curvature regions. So the mesh is very fine. So only the tetrahedral mesh option is available here. For 1D and 2D, you can able to deal with the same. Yeah, as you could see, this is how we're gonna measure the curvature regions. Okay, so mesh is fine, no need to worry about it. So I'll simply run the study to get the results for the static analysis. So whatever the analysis selected now, it is static, and with respect to these boundary conditions, it's gonna give me the results in the form of stress, displacement, and strain. If you want, you can even add the factor of safety. Okay, so initially you need to create the static study. So once you do that, you need to create the fatigue analysis study one more that I'll explain. So the chart, you could see it shows 113 megapascal. You can change the chart in the options. You can define the unit system as per your requirement, that is megapascal unit for the stress. And for the chart option, I'll set it to general and 5 decimal points so that I can easily read the stress values. Okay, it is good to see, right? The yield strength is within 100. Okay, the displacement, you could see it is 3.194. That's fine. Now I'll create a new study. Okay, that study will be the buckling analysis. As I said, I have the access to each and every analysis: the buckling, thermal, topology optimization, frequency, non-linear analysis, linear dynamic analysis, drop test, and the pressure vessel. So at the moment, I'll deal with the fatigue. Okay, the constant amplitude fatigue analysis, and the variable amplitude analysis, harmonic, and even we have the random vibration. So at the moment, I'm going to concentrate only on the uh, amplitude events with the defined cycles. Okay, I'll simply select it, and I need to define the event. So in the event, you may need to define the number of cycles, how much you need. So for this analysis, I'll consider 10,000 cycles. Okay, from the analysis type, I'll select the zero biased. You can deal with the fully reversed and the other methods, so I had explained these things in the basics. Okay, so I'll select the zero based at this moment. The loading ratio also you can define, so at the moment I don't want it. Okay, so I'll select the zero based, so it is from 0 to 1, in the sense 100 Newton, and again it will come to rest, and again the cycle will repeat. So the scale is 1 here, as we did in abacus. So you can even change the scale here. Later on we can do that. So first let me run this analysis. Okay, so in the fatigue options, you can define the study properties. Okay, so I'll showcase that one. So here you could see you can even select the computing type, and the for ductile metals you can select the Gerber. So I did the same thing. You can even select the Goodman as well if you're dealing with the brittle materials. Okay. Yep. As you could see, you'll get the message that the reducing success everywhere is just minimum than this and go, so there is no damage. So I'll simply run the study by just simply saying no. So it will calculate the analysis, give the results. Okay. So you could able to see the results. So this is the damage percentage, and this is the life. Life is e raised to 7, which is the high fatigue cycle, so which is safe. It is under the endurance limit. Okay. So now I'll change the event, and I'll just increase the scale factor to 2. So 100 Newton I had defined. If I increase it to 2, it will be multiplied by 2. It is 200 Newton. So you can run the analysis again to cross check the same whether it's gonna fail or it gonna attain the minimum 10,000 cycle within this range or not. Yep, again it shows the model are below the stress versus number of cycle curve. So it is safe enough. Again, you can even cross check. I believe it is e raised to 7, so no need to worry. So now I'll make it 5, so it is 500 Newton, right? Now I'll simply run the study. So once I do that, it should fail because the stress versus number of cycle curve I had defined as maximum is 380 Newton. So as you could see, it shows the the stresses in the model exceeded the maximum stress value. So whatever the curve which we have defined, the SN curve, it has already exceeded. So with respect to that data, if you want to complete, just say yes, it is saying. So I'll just say yes. So according to the SN curve which I had defined in the material data, according to that it will try to solve your model, and this is the damage area, the damage percentage result, and the life. As you could see, this is the region where it gonna fail, and the number of cycles are very less at the markings in the chart. You could see the blue indicates the number of cycle is very less at that area. For your convenience, I'll just refine the chart by just changing it to general and defining the decimal to 10. Okay, once you do that, you could able to see the color coding will change accordingly, and the maximum number of cycles is more than 10 raised to 6, and at this region it is 7,000 cycles, so which is minimum than our requirement. We had requested for 10,000, right? Yep. So you could able to see the SN curve here. So I'll just change the unit system to make you understand what exactly I have taken into account. So this is the value. The maximum stress is 318, at that region it is 7,000 only. So same thing, 135, it is 10 raised to 7. Okay, so this is how you can even feed your own data. Let's say your company has it, or from the vendors you will get this data, so you just need to enter into this particular column in the async curves, and you can easily access it to the fatigue analysis. Okay, yeah, so I hope you got the concepts which and all we have covered here. So this is how we need to deal with the analysis in the Solidworks. Yep, that's all about the session. Thank you all. Stay tuned. Bye everyone.